All right, so let's take this idea of a basis and and how it represents our that vector. Right, so we'll also include our x vector, which I forgot to include in here. So we had x was what was it, the vector 3, 2. So we're going to think about how we could take this basis, right? Because we've already established that if it's a basis, that I can create all of, ooh, don't know what I'm doing here. Ooh, stop. Not sure what I just did. Click some buttons. And those things happen. All right, so because it's a basis, this means that I can create all of R2 using these vectors. Okay. So if we think about so what I'm going to do, I'm going to put our traditional coordinate system in here. And I'm going to put it in gray here just so that it's sort of in the background. Okay, so this is our traditional IJ coordinate system or XY coordinate system. And I'm going to go back and I'm going to take those same two vectors. So I'm going to graph our 1, 2 vector, 1, 2, right? There we go. And our 5, -1 vector, 1, 2, 3, 4, 5, -1 vector. And we'll graph our 3, 2 vector, 3, 2 here. Right. Now, what we're going to do is I'm going to say, okay, well, I don't want my axes to be along the x and the y direction. What I want to do is I want to let my axes be along the, I'm going to call this one B1 and the B2 direction. So essentially what I'm going to do here is I'm going to create a new set of axes that look kind of like this. So here's my, oh God, that was a terrible, terrible line. Anyway, we call this, so this one's the B1 axis. And this one here is the B2 axis. The B2 axis. Right? And now, in terms of orienting ourselves along these axes, if I've gone a distance of one of our B1 vectors, this is kind of like, this is equivalent to one of our B1s. So this would be the new 1 in our coordinate system, right? And then if I go another length of B1 along that axis, this would be equivalent, and I'm putting it in quotations because this is kind of like we're translating. So what we're doing is we're going from what we typically define as our XY or as our axes, and we're redefining them as a new set of constants of 1, 2, 3, so on. And along here, right, you'll see, again, this would be 1 in the B2 direction. And then if I went in here roughly about the same, this would be a 2 in the B2 direction. Right? And then what I end up with is this sort of skewed grid here. Okay, if we add in our sub coordinates like this, right? And I can go either direction. As you can see, I can plot any particular point on this axis, and I can express that as as constants or as multiples of the B1, B2 axes. So our point here in our x and y coordinate system, this was our vector 3, 2. But we figured out in the last section, we figured out that in order to get x2 out of B1 and B2, right, I'd have to do, what was it, 13/11ths times our B2 times the 1, 2, and 4/11ths in the B1 direction. So 5, -1. I know I listed the 1, 2 first, but the order that those things are in the set doesn't make too much of a difference. It's just whatever you want, right? So this, if I take this equation, I'm going to get the vector 3, 2, right? Which means that this here on my coordinate system that I've now created using the B1 and the B2 vectors, right? This is the point 13. Nope. Try that one again. That was the 4/11ths, so this would be the point 4/11ths, right? Because I haven't gotten to the 1 yet. I don't need all of the B1 vector to get there. And this is the point 13/11ths, or that's 13/11ths of the way along our B2 axis. Right? So in other words, so this new vector here, so the vector in our B1 space, so in the coordinate system for B1, our x vector becomes, so this is, it's transformed into the vector, what would it be? If we're listing B1 first and then B2, it would be 4/11ths and 13/11ths, right? And that, yeah, it doesn't really matter. B1, B2, the order, whatever, it doesn't matter. There we go, right? So this would be a B1, B2 axis, based on how I numbered them, how I define them. This thing, this is our x vector in B. So this gets a new name. So we call this, instead of calling it the x vector, this gets the symbol, the x vector in B. And this is defined using something else. Now, if we take this vector equation here, right, and we boil it down to, we could combine this and rewrite it, you'd see that if we take this as a vector equation, all right, we're going to switch this around. Sorry. So sorry. We'll put 4/11ths here. And nope, I lied. I want 13/11ths and 4/11ths. And you know what? Just for fun, we'll, goodness me, oh my. For fun, we'll rename that. We'll let that be B2 and that be B1, right? Doesn't really matter. I guess that makes more sense if we go based on the order that I have those in. It makes more sense to call that the B2 axis and the B1 axis. But again, we're creating these. We get to decide what to call them right now. But for the sake of the way that I actually wrote this equation, and it really doesn't matter, do you see how I could take this as the matrix 1, 2, 5, -1, and multiply it by the vector 13/11ths, 4/11ths? And that would give me my vector 3, 2 in our standard. So this is our standard. This one here is the matrix, or this is the coordinate vector in B, or the B coordinate of X. And then this thing here is kind of like is the matrix that's made up of our B1 and our B2 vectors, or this is the matrix made up out of the bases. So this leads us to some definitions here. So whatever however we are able to transform a standard vector into a new vector in our new coordinate system, we call that the B coordinate of X. And it has this notation here. Right? So we have the X vector, it's a vector made up of X in the B coordinate system, and it is made up of the coordinates that are going to give us the linear combination of our B1 and B2 to give us what X would be in our standard system. Right? Now, this transformation or this mapping, we define it this way. So we notice this new little symbol here. So it's not just an arrow, it's an arrow with a little, so this means a mapping. So they're not equivalent. This is saying that I'm taking my X and I'm transforming it into a new vector in my new coordinate system. Right? So I'm mapping my standard vector into a vector determined by our B coordinate system. Right? The change of coordinates matrix, right, which was, if you saw up here, we multiplied the that if I take that 13/11ths and the 4/11ths and I multiply it by the matrix made up of our vectors, that's called the change of coordinates matrix, and we call it P sub B. Just go with it. I don't know why it's P. It is. And that's made up of, so this just means this is the B1 vector, so it's the matrix made up of where the columns are the vectors that define the basis. And then lastly, we have this idea of the change of coordinates equation. So the change of coordinates equation, right, if you see up here, this here, so we called x in our thing here was 3, 2. We defined our b coordinate of x to be 13 elevenths, 4 elevenths. Our change of coordinates matrix was 1, 2, 5, -1. And if we put that together in the equation that we had, do you see how we found x, or x was a result of taking our PB matrix times our b coordinate of x vector. And so here we go. So there's our equation there. So this leads us to how to get x if I have my b coordinate of x. Well, if we take this vector equation, all I need to know, I get x by multiplying. So there's multiple ways. So the first thing I could do is I could take PB, or our change of coordinate matrix, times that x coordinate of b, and that'll get me x, right? So I could do it through multiplication. Or if I take the, if I have x sub b, I can define x sub b as the, oh, where do I have it? My brain. Or I could solve the augmented matrix of the inverse of my PV matrix augmented with my x of b, my x coordinate of b, or b coordinate of x. Let's try that again. All right, so if I do that, right, because if you think about it, right, that's one way to solve for x sub b. Right, you ready? Ready? If I multiply both sides by the inverse, b inverse times x is going to equal my x coordinate of b. So if I have x and I want x of b, I can do this a couple ways. I can multiply x times my p. Oh, and I have to put that in the right order, don't I? Right, matrix first, then the vector. So if I take the inverse of my change of coordinates matrix and I multiply that by my x vector, that'll get me my coordinate of x, b coordinate of x vector. Or I can solve the augmented matrix of just my regular, right? So we're trying to get this. So if you think about this as ax equals b, we can take this and augment it with our x vector, right? This is a very, very, this is a form of our matrix equation ax equals b. So how we would normally solve for the parts of this apply here, right? So same processes that we've already done, we're just putting new names to things and we're using it to represent a different space. Hope that makes sense. Okay, let's do some examples. So here's our first example. So here's our here's our basis. So our basis is 2, 1, -1, 1, and our x is 4, 5. We want the b coordinate of x vector. So we can get that a couple of ways, right? We can augment, or we can find an inverse. So first we need a couple of things. We know that our, and I'm going to forget the names of these things, but our change of coordinates matrix, PB, is what happens when I take the matrix of my vectors. And we know we have the equation that x equals PB times x, the x coordinate of, or the b coordinate of x. The order there, order. All right, so I could find the inverse to isolate this, or we could take what we typically do for ax equals b and augment the matrix A and B to get x. So we can take our PV matrix, our 2, 1, negative 1, 1, augment it with our x matrix, 5, 4, and do our lovely bit of coconuts here. And we're going to get down to 1, 0, 0, 1, and 3, 2. So what that means is that in our new coordinate system, the point defined by the standard vector 4, 2 is now going to be defined by the vector 3, 2. Right? So that means that our b coordinate of x is 3, 2. And if we think about this graphically, so if we go back and look at it graphically, and again, I'm going to put this in standard form to begin with so that I can at least, 1, 2, 2, 1, 2, 3, 1, 2, 3. Oops, 1, 2, 3, 4. I need to get out 4 that way. 1, 2, 3, 4, 5. I need to get 5 that way. All right, so here's our x vector. 1, 2, 3, 4, 5. Okay, so there's x. And that x is going to make, like, it's still going to get us from the origin to that point in space, but it's going to get us to that origin, to that point in space in a different way. It's going to use the 2, 1. So here's one of my axes, right? So this is going to be my B1 axis. And then negative 1, 1. This one here, this is going to be my B2 axis. And do you see how if this is B1, if we take another 1, 2, or only 2, we really only need 2, right, of those. 2 of those going to get me there. And if I go, new color, we'll go back to green. 3 of these, right, 1, 2, 3. 3 along this way, I get this one here. And this point, you see how I've gone 3 in the B1 direction. So 3 B1s and 2 B2s is going to get me this point here. So kind of, hopefully that makes sense. So we're still talking about the same point, but what we've done now is we've shifted what our orientation system is, which means that the expression or what we're listing that point as is not the same. It's the same idea. If you've ever studied chain bases in numbers, like base number systems, so like binary, right? In binary, we count everything by 2s, and we get to a new basis when we get to 2s. When we get to 2, so like 2, 4, 8, all those kinds of things. Same thing with like hexadecimal. If you're into hexadecimal, there's 16 things that represent. If you know French, French is the French language for numbers uses a base 20 system. So like if you think about, if you count up in French, every set of 20 is when you get to a new definition of like a whole kind of thing. Not a whole, but like our typical system is a base 10 system, right? Which means that to get to the next place value, we need to, I have to get to the next 10, right? And a base 2 system means you get to the next 2 and that gets you to the next place value. So this is the same kind of idea as a different base coordinate. So I'm just going to stop there. All right, let's move on with some theorems, some isomorphisms, some quick little definitions over here on the side that we sort of haven't talked about yet, but hopefully they kind of intuitively make sense. So a theorem says that if our basis, so we have this vector, this basis defined for a vector space B, then our coordinate mapping of x onto the b coordinate of x is both 1 to 1 and onto. So we kind of need to understand what one-to-one and onto mean. So onto means that I have an output for every single input. So for every input that I put in there, I'm going to have an output. That kind of makes sense. So, and it has to be, so something that's not onto, if you think about in the real number system, so not thinking in vectors, but the function natural log of x. So natural log of x is not defined for all of the real numbers. So natural log of x is not onto because I cannot put every single possible x in the known universe. So I cannot I have to limit this. So right, x is not an element of all of our, it's x needs to be greater than 0, or no, greater, right? I can only put positive numbers greater than 0 into natural log, which means that it is not onto, right? So because this is not all of r, that means that it's not onto. Versus e to the x, right, which is sort of its converse or its inverse, e to the x is onto because for every, because I can put any x in the real number system into e to the x and I have a defined output. Hopefully that makes sense. One-to-one means that I'm not going to get a repeat of any of my outputs for any of my inputs. So something that is not one-to-one is x squared, right? For, again, thinking in our real number system instead of our linear algebra system. X squared is not one-to-one because both x equals 1 and x equals -1 give the output of 1, right? So both of those map to the same value or the same output. So because of that, they're not one-to-one. So in terms of our transformations, what that means is that to be one-to-one, that means that each one of our images or all of our output vectors can't repeat themselves. So whatever vector I put in, if I put in 2 different vectors, the outputs have to be 2 different vectors. They can't be the same vector. All right, that's what one-to-one and onto means. So what this is saying is that if B is a basis for my vector space, then this mapping from the coordinate system that we're used to our B coordinate system is a one-to-one linear transformation, right? So that means that everything is going to have its own unique output. So we argued that this was a basis for P3, or in other words, we argued that S, where we talked about it in the general sense up to an nth degree polynomial, was a basis for P to the n. So we want to show that P3 is going to map onto R4. So we can use this theorem to say, essentially, so we want to do the transformation. So our domain, so our transformation is going to take the domain of P3 and map it onto the codomain of R4. And what we want to show is that P3 is going to map onto all of R4. So what I'm going to do is I'm going to define S in terms of the span, right? So we know that the span of this is that all S, or nope, there we go, polynomials of T here are, let's put the polynomial there, or the vector there, our polynomials of T are some constant a1 or a0 plus a1t plus a2t squared plus a3t cubed. Now we don't have to keep going any further because those are equivalent. Now if I put this into, so these are solutions, this is every single possible polynomial that we could get from this basis. If I express this in vector form, we can get that our standard basis, if we just take the constants, right? So what we want to show is that P of t maps onto the P basis, there we go, for the B coordinate of P. So the vector of the constants, right, our P basis of B is the vectors A1, A2, A3, A0, A1, A2, and A3, right? This, because it has four elements, is an element of R4, and hopefully it's not hard to argue that because I don't know what A0, A1, A2, and A3 are, that this, so every possible vector is in here. Vector in R4 is in here. Okay. That's it. All right, that's hopefully that makes sense. All right, just a smidgen of hair left. These things are actually called an isomorphism. So if I can show that my linear transformation, that I have a one-to-one linear transformation that takes vector v and maps it onto vector w. So in other words, my transformation, oh goodness. If my transformation that takes v onto w, and v and w are the exact same space. So the onto means it has every single, that every input has an output. And the one-to-one says that every input gives me a unique output. What that essentially says is those two spaces are equivalent kind of spaces. So the one-to-one and onto says that these two things, we call this an isomorphism of V onto W. So V and W in this case are isomorphic. And what that really kind of means is that they're the same space, but they look a little bit different, right? If you think about our basis and our vector space and how they're defined, and that isomorphic thing, they're representations of the same place. So to be isomorphic, or two vector spaces are isomorphic. Vector spaces are isomorphic if they represent the same vector space, but the elements in each look different. So up here, right, P3 and R4, the elements in those things look very, very different. In P3, it looks like a bunch of polynomials. In R4, it's vectors that have four elements in each vector. So the things that make up each of those are different, but they represent the exact same space. And also, if you take the Greek representation here, in Greek, iso means the same, and morphic or morph in Greek. Anyone just have a Power Ranger moment? I did. In Greek means either form or structure. So this word isomorphic means that they have the same structure, but they're not exactly the same. All right, so this last example isn't necessarily related to this idea of isomorphism, but it is just talking about this P2 space and whether or not these particular polynomials are going to be linearly independent or linearly dependent. So what we want to do is we want to express these in a in vector format and be able to show that the coefficients that make up each of these polynomials are, so in other words, instead of R, so we'd have, these would be R3, right? So each of these vectors, I can represent this as a vector in R3 that is a mapping from P2 2R3. So this would be the vector 1, 0, 2. This next one is the vector 4, 1, 5. And the last one is the vector 3, 2, 0. And if I augment this with the 0, 0 vector, so I want to show linearly dependent, so we need AX equals 0 to show our linear independence. And if I get anything other than the trivial solution, which it turns out I do, if we get this down to this point, 0, 1, 2, 0, 0, 1, 2, 0. Hopefully you can see that because these two rows are the same, what that's going to do is that's going to say that I have a free variable. Oops, I have a free variable. Therefore, these columns are dependent. They are linearly dependent. Ta-da! So I can use two of them to make the third. In other words, essentially, if I can do some combination of the first two polynomials to give me that second polynomial. Ta-da! Third polynomial. All right, that's it.